We all know that air conditioning units can provide cooling, but we can use the low boiling point of the refrigerant as well as some clever valves to provide both heating and cooling at the same time. I'm going to show you how that's possible in this video, which is sponsored by Danfoss Climate Solutions. If you want to see a VRF unit in action, you should check out Danfoss's ETS 5M range, which is ideal for high evaporating temperature crack units with direct expansion. The new valve is electrically compatible with existing 12-volt drivers and is a major addition to the portfolio for small AC units, as well as extending the well-established portfolio of components for crack units, which include compressors, controls and sensors, system protectors like filter dryers, ball valves and check valves, and also microplate heat exchangers. Do check them out. I'll leave a link for you in the video description down below. VRF stands for Variable Refrigerant Flow. They come in many different sizes and designs, but these are more advanced than a standard air conditioning unit because they vary the amount of refrigerant flowing around the system. We'll see how that works later on in this video. Typically, a refrigeration system will only provide cooling, but a VRF unit can provide cooling, heating, or a mixture of heating and cooling at the same time. We often find them used in offices, hotels, retail, education, and healthcare facilities. That's because they have different heating and cooling demands within these type of buildings. Imagine a hotel. One guest might want heating, and another might want cooling. That would require a separate heating and cooling system, which takes up a lot of space. It costs more to install, it requires a lot of maintenance, and also wastes a lot of energy. Instead, we can use a VRF unit to remove the heat where it's not needed and transport this to where it is needed. Where have you seen VRF units used? Let me know in the comment section down below. So we have four main parts in a basic refrigeration system: the compressor, the condenser, the expansion valve, and the evaporator. These are all connected via a pipe. Inside the pipe is a refrigerant, which is a special fluid which can easily convert between being a liquid and a gas. The compressor squeezes the refrigerant into a small volume and pushes it around the entire system. The condenser and the evaporator are both heat exchangers, which allows thermal energy to transfer between the air and the refrigerant without them coming into direct contact with each other. One unit sits inside the property and the other sits outside. The refrigerant leaves the compressor as a high pressure, high temperature, superheated vapor. We call this the hot gas line. The refrigerant then passes through the tube of the condenser. The refrigerant inside the tube is a much higher temperature than the ambient air surrounding it. That's done on purpose because heat flows from hot to cold, and we need to remove the heat from the system. So the system needs to be a higher temperature. The heat will flow from the refrigerant through the tube wall and into the air. A fan blows the ambient air over the tube to help speed that process up and remove more heat. As the thermal energy is removed from the refrigerant will condense into a liquid, similar to how steam condenses into a liquid on a window on a cold day. By the time the refrigerant leaves the condenser, it will be a high pressure, medium temperature, saturated liquid. We call this the liquid line. This then flows to the expansion valve. We generally find either a thermostatic expansion valve or an electronic expansion valve. And by the way, we have covered how these work in detail in our previous video, links down below for that. These valves use a sensor and controller to measure something called the superheat at the exit of the evaporator. The valve will then open or close to restrict the flow of refrigerant into the evaporator in order to try and maintain a constant superheat value. Superheat basically means the refrigerant is heated to a point that it is completely gas. No liquid is present at that point. So we have high pressure, medium temperature, saturated liquid entering the expansion valve, and then a low pressure, low temperature, liquid vapor mixture leaving the expansion valve. The refrigerant drops in pressure and temperature because it is expanding in volume. Much like when you spray a pressurized liquid through a nozzle, the contents will exit as a mixture of liquid and vapor, and we feel the container become cooler. This will then flow through the evaporator, which is located inside the property. The refrigerant has a very low boiling point, so the heat of the room is enough to boil the refrigerant, and as it boils, it turns into a gas which carries the unwanted heat away. By the time it exits, it will be a low temperature, low pressure, and slightly superheated. The refrigerant is sucked into the compressor, and liquids cannot be compressed. If liquids enter the compressor, they can damage it. So we allow slightly superheated refrigerant into the compressor. This line is called the suction line. The problem we face is that the cooling load varies. Under low load conditions, the compressor still has to run, but less refrigerant can pass through the expansion valve. So the pressure increases as the refrigerant backs up in the system. So what can we do about this? One method, known as unloading, opens a solenoid valve to recirculate refrigerant back into the compressor until the pressure decreases enough. This is very inefficient because the compressor is running to push the refrigerant, but it is just being recycled and is not providing any cooling. Another method is to simply turn the compressor off when the pressure is too high and then turn the compressor on again when this drops. The problem here is that it causes surges in pressure, resulting in poor thermal control. Additionally, there will be a surge in electrical current when the compressor turns on. Both of these reduce the working life of the compressor. A VRF unit uses an inverter to change the speed of the compressor so that the volume of refrigerant flowing around the system changes to match the current cooling demand. As the expansion valve restricts the flow of refrigerant, the pressure increases and the compressor reacts to this by slowing down, resulting in less refrigerant being pushed out and around the system. So the energy consumption of this system is far lower and we get optimal thermal control. We can then connect multiple indoor units to a single external condenser. Each indoor unit has an expansion valve. The compressor changes its speed to suit the system requirements as these open and close. By the way, we have also covered basic HVAC controls previously, links down below for that. Heating-only VRF systems aren't very common, but they are essentially just an air conditioning system running in reverse, absorbing heat from the outside air and transferring this indoors. So this is basically just a heat pump. But how would this work in winter when the air is cold? Well, the refrigerant has an extremely low boiling point. Take R410A for example. It boils at negative 48.5 degrees Celsius, whereas water boils at around 100 degrees Celsius. These figures do change with pressure, but as long as the air is above the boiling point temperature, it will cause the refrigerant to boil, and so we can absorb thermal energy from the air. You can see this vessel is filled with a liquid, and using just the heat of my hand, I can cause it to boil and evaporate. It will then condense back down into a liquid as it cools. So even in winter, we can pick up thermal energy from the outdoor air. The compressor will pack this into a very small volume, which will increase the temperature and pressure up to a usable level, and this thermal energy will then be released into the room. Obviously, the colder the air, the harder it is to collect this heat. We usually want a system that can provide cooling in the summer and heating in the winter. For that, we need a reversing valve. This has a sliding connector inside. There are many ways to achieve this, but in this example, we will use 2 expansion valves and 2 check valves. The hot gas which is discharged from the compressor is sent into the reversing valve. In heating mode, the valve slides across to send the hot refrigerant straight to the indoor heat exchanger to provide heating. It then flows through one check valve, but the second valve blocks the flow, so it has to flow through the expansion valve. And from there, it can flow to the outdoor unit where it picks up more thermal energy and then returns to the compressor. In cooling mode, the valve slides across and the hot gas is sent straight to the outdoor unit where the thermal energy is removed. It then flows through a check valve and the other expansion valve before entering the indoor unit where it absorbs the heat of the room and thus provides cooling. The refrigerant then returns to the compressor. We often find multiple units connected together within a commercial building. With this setup, all units can provide heating or all units can provide cooling, but importantly, some can provide heating while some can provide cooling at the same time. Each indoor unit is connected to a branch controller, which contains a number of valves to direct the flow of refrigerant to provide either heating or cooling. In this system, we have 3 pipes running to each branch controller: the suction line with the superheated gas, the liquid line providing cooling, and the hot gas line providing heating. We also have a variable speed compressor located outside. In cooling mode, the compressor sends the hot refrigerant to the outdoor unit to reject the heat. This will then flow to each of the branch controllers, where it flows through an expansion valve and then through the indoor unit to provide cooling and also collect the unwanted heat. It then brings us back to the compressor. In heating mode, the compressor sends the hot gas to the indoor units, where it provides heat to the rooms and then flows to the outdoor unit, where it will flow through an expansion valve before entering the outdoor unit to absorb the thermal energy of the ambient outdoor air. This then flows to the compressor so that it can be compressed up to a usable temperature and pressure and then sent around the building. In mixed mode, the hot discharge of the compressor is sent to both the indoor unit as well as the outdoor unit. When it flows to the outdoor unit, it will then flow to the units requiring cooling. This will then flow back to the compressor to repeat the cycle. Meanwhile, the compressor is also sending hot gas to the indoor units which are requiring heating. The refrigerant exits these units and will flow to the units requiring cooling. So that way, the same system can provide both heating and cooling at the same time. If we consider a larger system with multiple indoor and outdoor units, in full cooling mode, all indoor units are collecting heat and all outdoor units are rejecting heat. In full heating mode, all outdoor units are collecting heat and all indoor units are rejecting heat. And then in mixed mode, if 2 indoor units require heating and 2 require cooling, and the loads are equal, then the outdoor units are not used. The thermal energy is simply transferred between the units, so we have a full heat recovery. The compressor still runs to push the refrigerant around the system though. If the heating and cooling loads are not equal, and we have, for example, 3 indoor units providing heating and 1 unit providing cooling, then we will need to run some outdoor units to collect more thermal energy, as the single indoor unit in cooling mode will not be able to collect sufficient thermal energy to provide the other units with heating. Check out these videos to continue learning about refrigeration engineering, and I'll catch you there for the next lesson. Don't forget to follow us on Facebook, LinkedIn, Instagram, TikTok, Twitter, and theengineeringmindset.com.